Our next speaker is Zhuihui from the New Jersey Institute of Technology. Zhuihui is going to talk to us about minimum mapping-based connected components algorithm.
Okay, thank you. I'm Zhuihui from AGIT. I'm glad to present our work, minimal mapping-based connected components algorithms. First, about connected components, it's basically a graph partitioner problem. The basic idea is like for given graph and directed graph, we need to partition it into several subgraph. For each subgraph, all the vertices must be connected with with each other, and for any two subgraph, the vertex cannot have overlap. This is a connected component problem. Because a component is a basic unit of the graph, basic structure, and at the same time, for many other graph algorithms, they must work on connected components. So the connected components algorithm is very important. It's a basic graph algorithm. Here is a very simple example. For the existing connected components algorithm, I divided them into three methods. The first is based on graph traversal. For example, the label propagation or BFS-based method, they can have very good performance when the graph diameter is very small. But for very large graph diameter, the performance often is very bad. Another is the tree-based method. It abstracts the problem as a tree building problem. Use different hooking or compressing method to build a tree to represent different components. The third method is a disjoint set-based method. The sequential disjoint set-based algorithm are very fast, often approximately linear time. They will operate on the graph using different unified operation. And finally, the disjoint sets will represent the final component. For our method, we abstract the problem as a counterline, meaning that we will map the different vertices to different counterlines. Our minimum mapping operator is very simple. For a given edge, U and V, first, we find the minimal label of the ancestor. And second, we remap the minimal label to all the other descendants. This is the basic operation of minimal mapping. Our method, we have proved that our algorithm can convert in log-n time. So the feature of our algorithm is that first, it's very simple. The operation, very simple. Get the minimum value, assigned to other nodes. Second, it's very easy to parallel because you just work on different edge in parallel. Repeat the minimum mapping operation, and then you can get the final result. The algorithm is just like this. First, we initialize the label array. We repeat on all the edges using the minimum mapping operator until the algorithm converges. This is the basic idea of our method. Here is the example. We work on a very special graph. It's just a line. We show how our algorithm can convert in log-n time. Finally, we map all the vertices on the line onto the minimal label 0. We have implemented our algorithm into different kind of packages and language. First, we integrate into Acuda. At the same time, we also implement another typical and highly optimized connected component algorithm, FastSV, in CHIUW. At the same time, we developed different variants of our algorithm, C1, C2, CS, CES, synchronized method, just based on using different kind of searching steps, different kind of assignment method to show the difference. We also implement our method in the high-level LA graph package, compiled their FastSV method. And in the low-level graph package, GBBS, they have a simplified and highly optimized SV method. We compile our method with a C++-based method. Here is the experimental result. We test our algorithm with the comparison algorithm on real-world and synthetic graphs. First, for the iteration number, total number of iterations, we can see that our counter method can achieve the minimum number of iterations compared with the compiled FastSV method. At the same time, we can also see that for the performance compared with FastSV, our counter algorithm can achieve speed up more than 2 times performance, sometimes close to 8 or much better. This is the one local testing result. At the same time, we also test our algorithm using multi-local. Here is a 4 local based method. We can see from most of the testing results, the traits are same, just like the 1 local method. But one result is very different. It is a C1 method. It means we just, for our minimum mapping method, we just search 1 step instead of the default 2 step. For C1 method, the multi-local method can achieve much better performance for the low diameter graph. Even the total number of iterations are very large. The reason is that for multi-local method, the communication cost is very is a bottleneck. So for C1 method, the remote access or communication volume is minimal. So this is why C1 method can achieve much better performance for multi-local result. Here we give some other implementation result. We use Delunen 20 graph as an example to see the absolute execution time. What's the difference for the different kind of package, different kind of language? First, for CHIUW, we can see that our method can achieve about more than 7 times speed up compared with FastSV method. But on the LA graph package, we cannot achieve speed up. Our performance is just like the FastSV method. The reason is that we can only use the graph-less interface. This interface, we cannot explore the flexible and fine-grained paradigms. And so the performance of our control algorithm cannot beat the FastSV method. For another low-level graph package, GBBS, it's a C++ package. Our counter method can achieve about 2 times speed compared with the optimized SV method. This result show that first, our counter algorithm can beat the fast SV method if the language or the package allow us to explore the parallelisms efficiently. At the same time, we can see that the absolute execution time used CHIUW is much larger than the C++ and the C-based graph package method. So the conclusion is that we provide a very important and high connected components algorithm, counter algorithm. It's easy, very easy to parallel, and very simple, but it can achieve high performance. We have proved that it can converge in log-n time. For other methods, they cannot have this result. Second, compared with CHIUW, we can see that CHIUW have performance overhead compared with the C++ method, but the CHIUW have can explore the fine and the flexible parallelisms compared with a high-level LA graph package. Compared with GBBS, it's a shared memory package. CHIUW can support distributed parallelisms, but GBBS cannot. But the absolute performance of GBBS is much better. We thanks the CHIUW and the Akuda community help us to integrate our method into Akuda, and we thanks the NSF for the funding. Thank you for your listening. I'm ready to take your questions.
Thanks, Zhuihui. Has anyone got any questions for Zhuihui? So I might start while people are thinking. So I didn't quite understand where the overheads for CHIUW were coming from. Were they coming from communications, or were those overheads you mentioned when you showed that the CHIUW code was 10 times slower than the C codes? Was that purely for a single locale, in which case it's not communications?
There are two aspects. First, compared our experimental results on different kinds of graph algorithms show that the multi-locale method often is much slower than the single locale method. It means that the communication overhead is very high for CHIUW. This is one aspect. Another aspect is because of the language. Compared with the C and the C++ package, our performance data, we just test the kernel part, do not include the starting part, ending part, something like that. Even this, we can find that the CHIUW overhead is high compared with C and C++ package. So I'm also a little bit confused about this result. It seems that the kernel part is just some array operation. I also cannot understand why CHIUW has such high overhead. Yeah.
Sounds like a good mystery to work on with the CHIUW team, and maybe others who are interested in helping.
Yeah.
Thanks.